Well, come on in. Welcome. Grab your notebook. Get your pen, pencil ready. Whatever you want to write with is fine. This is math from the void. Math coming at you out of nowhere. And here we have a very similar problem to some BC level problem that we've worked on, and that's because they're from the exact same year. But the two questions are slightly different in difficulty. However, we still have a situation. And so if you were wondering how to do that previous problem, if you're an AB student, at least you have your own little Quartic oil tank problem to do. The questions are slightly different in what they're asking you. We don't have to take into consideration the weight of the oil, for example. But here, nonetheless, we have an oil tank, which is basically shaped by revolving this Quartic function around the y-axis. And since it's revolved around the y-axis, that tells us that we're probably going to need to use dy at some point, like x equals a function of y at some point. Okay, x and y measured in feet. Great. Oil flows into the tank at the constant rate of 8 cubic feet per minute. So cubic feet is a measurement of volume, but it's a rate. So this is the change in volume, dV, over time, dt. And they're telling us that it is 8. All right. It's almost like saying gallons per minute, but cubic feet is just a different measurement for volume. Okay. Find the volume of the tank. Indicate units of measure. Okay, so for this, we definitely need to take an integral. I want you to imagine the sort of layers of the tank, like if it was being 3D printed. Maybe that doesn't help you visualize it at all, but it would do it sort of two-dimensional plate at a time. You would have these like circular discs, right? And the radius on each of those discs, in fact, let me draw it to the side. Whenever you're trying to calculate volumes by using integrals like this, it's really good to get a cross-sectional shape. The center is the y-axis, and the radius at any given time is just the x value. So we need x to be a function of y because the thickness of these discs is this little thickness dy. Okay, so let's get this solved for x, because the area of one of these discs is pi r squared, or I guess in other words, just pi x squared. So if we can find out what's x squared, then in terms of y, then we can integrate it with respect to y. Make sense? Okay, so let's take this, and we're going to multiply both sides by 625 and divide by 9. That's going to get the y with some buddies here. And this is x to the 4th. So we just take a square root. Fortunately, those things are perfect squares. Oh, except for the y. So we're going to have 25 over 3 times the square root of y equals to x squared. So we don't even need to solve for x. We can just plug that in as x squared, right? So 25 over 3 times square root of y. We're not going to square that. That is what x squared is. So 25 over 3 square root of y. That is the area of one of the discs. So if you tell me how high the disc is, I can tell you what the area is of that slice of that disc. It can be down here. The lower ones, these are smaller, obviously, because the tank is not as wide at that point. And then the biggest of these slices is the very top layer, which has the largest slice because the radius is a maximum. See how the radius is getting bigger as we go up this curve. It's going further out to the right, to the side. Okay, so we need to find that volume. We're almost there. And it also says indicate units of measure, which means that you get some points for that. Do not forget the units. We're basically just going to integrate this from what to what? From 0 like from the y equals 0 at the bottom all the way up to 9. So we're going to integrate. We can bring all of this stuff out. 25 pi over 3. We don't need that inside the integral. From 0 to 9, y to the 1/2 power dy. So this is going to give me 25 pi over 3. And then anti-differentiating gives me 3/2 power. Divide by that, which means flip it. Multiply by 2/3. And this is going to be evaluated from 0 to 9. If we plug in 0, of course, we just get 0, so there's not really anything interesting there. But if we plug in 9, this on the top is 50 pi over 9. And then we have 9 to the 3/2. So we have to do the square root of 9 first, which is 3. And then we cube that, which is 27. So this is the same as 27. And that will cancel a bit with the 9. Leaves us with 150 pi. 50 pi times 3. And what are the units? They told us the volume units earlier. They said cubic feet. So that's how many cubic feet. So that's a lot of cubic feet. It will take a while. It will take some time to fill that up, that's for sure. Here we go. To the nearest minute. How long would it take to fill the tank if the tank was empty initially? Okay, well, 150 cubic feet. 150 pi cubic feet equals the rate, which is just 8, multiplied by the time. So it's 8 cubic feet per minute, but how many minutes does it take? And it wants it to the nearest minute. Let's figure out what 150 pi is. I guess I'll use like that. That seems like plenty to use for pi, right? Let's just multiply it by 15 and then put a 0 on it at the end. So let's see, this is 45, 4, 29, 9, 3, 8, and 5, 13, 21, 22. I'm just multiplying, don't worry. 7, 11, 15, 16, 17. Okay, there we go. So 1, 2, 3, 4. We're only going to go 4 decimal places. And that'll give us times 150. So this, if we divide this by 8, that'll give us the time. I know it seems like this is a long-winded process, but I think you might be able to use a calculator on this section. I'm not really sure, to be honest. But let's just assume not. I don't really like using them, to be honest. 64, 72, that's a nice one. 9, so we get 72. This is 0. That's a 3, which means 0, then an 8, so a 4. Then a 6, 5, so that's going to be 8. And then 1, 2, 5. So to the nearest minute, I guess we didn't have to even go that far. I'm sure if we would have used like 3.14, probably would have been fine. But, you know, just to make sure. So this is going to say at 59 minutes. Okay, part C. Let H be the depth in feet of oil in the tank. Okay. How fast is the depth of the oil increasing when H equals 4? Got it. So they basically want to know the rate. So how fast is the depth of the oil increasing? So this is like dH dt is really what they're looking for. When H is equal to 4. So we have to find a way to extract dH dt somehow. But we also need to consider the volume, right? So the volume is given by this integral from 0 to h. 0 to 9 was the volume of the entire tank, but just from 0 to h. Integral from 0 to h of, what was this, 25 pi over 3 square root of y dy. We want to find out how fast the height is actually changing. We're going to need to take a derivative with respect to t. So we're going to take a derivative of this integral. And you guys know what happens when we take the derivative of an integral, right? We basically just replace the limit here, the variable limit, into there. We do have to consider the chain rule. Like if this were h squared, it would technically put an h squared in there, but then we would still have to multiply by 2h. So we would still have to follow the chain rule. I would definitely mention that if we needed it. But other than that, we're just saying this is 25 pi over 3 times square root of h. Yeah, that's it. And we know that dv dt, the rate of change of the volume, is actually equal to, oh, whoops. I just said we have to consider the chain rule, didn't I? We do have to consider the chain rule because we're taking a derivative with respect to t. So this is going to be 25 pi over 3 times square root of h dh dt equals to 8. Now, at the moment when h equals 4, that's where we're able to use this information. At the exact moment where h equals 4, that's going to determine how fast the height is rising, if we know how fast or how high it is at that moment. So square root of 4 is just 2. This is 50 pi over 3 dh dt equals 8. So then we have to flip multiply everything over there. So the dh dt is going to be 3 times 8, which is 24, over 50 pi, which we can actually reduce that, can't we? Yeah, we can call this 12 over 25 pi. And that is exactly how fast the height is changing at the exact moment when the height is 4 feet. Does it say to indicate units of measure? Ooh, don't lose points on that. Indicate units of measure. So this is a change in the height. So this is basically just feet per, what was it, minute? Yeah, because these rates are measured in change over minutes. Okay, that would get you full points for this related rates problem. So this one is more clearly a related rates issue, but there's some integral in there as well. So hope you got something out of it. Make sure, as a note here, that when you have to calculate volumes, you're prepared to write the cross-sectional area, which means like the slices that we're adding up. Write them off to the side, figure out what area you're trying to deal with, and then integrate. All right? That's my best advice with these problems. Short and sweet. It's enough blabbing out of me. See you guys next time in the void.